Hello everyone, and welcome. My name is Dr. Fahmy, and today we are going to explore the essential world of pharmaceutical analysis frameworks. This session will serve as a master reference guide for understanding how we identify, determine, quantify, and purify pharmaceutical compounds. Think of this as learning the detective skills that ensure every medicine is safe, effective, and consistent. In pharmaceutical analysis, every test we perform is designed to answer one of two fundamental questions. The first question is a qualitative one. What specific chemical compounds are present in this sample? In other words, we ask, what is it? The second question is quantitative. What is the exact mathematical amount or concentration of the target substance? Here we ask, how much is there? Both types of information are critical because knowing the identity of a compound without knowing its strength is useless, and knowing the strength without confirming identity can be dangerous. Quantitative analysis is not a one-size-fits-all process because the amount of sample you have dictates the method you must use. At the micro scale, we are dealing with less than 1 milligram of material, which requires high-precision analysis for trace elements or highly potent compounds. The semi-micro scale covers 1 to 100 milligrams and represents the intermediate zone for standard pharmaceutical testing. Finally, the macro scale involves more than 100 milligrams and is used for bulk substance analysis and formulation validation. Choosing the correct scale from the start prevents costly errors and wasted effort. This slide outlines the 3 pathways for quantitative measurement in pharmaceutical analysis, even though they are organized under 2 main categories. Let me clarify. First, we have the gravimetric pathway. This method measures the exact weight of a precipitate or compound to determine its concentration. It is one of the oldest and most direct forms of quantitative analysis. Second, we have the instrumental pathway. This is a broad category that utilizes advanced equipment to measure physical properties. Under this umbrella, we find electrochemical methods, spectroscopic methods, and separation methodologies like chromatography. Third, we have the volumetric pathway, also known as the titrometric pathway. This method measures the specific volume of a standard solution required to completely react with the analyte. You will sometimes see volumetric analysis grouped separately, and sometimes it is considered part of the instrumental pathway depending on the detection method used. For our lecture today, we are going to focus more on the volumetric pathway first, because it forms the foundation of classical quantitative analysis. Then we will move into separation methodologies like chromatography, and finally we will spend significant time on spectroscopy, which falls under the instrumental pathway. So think of this slide as our roadmap for the entire lecture. Volumetric analysis, often called titration, is essentially a controlled chemical reaction performed in a laboratory. You add a solution of known concentration, which we call the titrant, to an unknown sample until the reaction is complete. The volume of titrant required to reach completion tells you exactly how much analyte was present in the sample. You can think of it like adding lemon juice to baking soda until it stops fizzing. The amount of juice you use tells you how much soda was there. It is a simple concept, but it is incredibly powerful. For titration to work correctly, 4 conditions must be met without exception. First, the chemical reaction must be stoichiometrically simple, meaning it follows one clear and predictable equation with no side reactions. Second, the reaction must be inherently fast, or we must be able to accelerate it reliably using a catalyst. Third, the reaction must reach 100% completion, with no reversible equilibrium hindering the final measurement. Fourth and finally, the system must have a distinct and observable endpoint, such as a color change from an indicator, to signal the exact moment the reaction concludes. If any one of these conditions is missing, titration is simply not a valid option. Titrations fall into 4 main classes based on the type of chemical reaction involved. The first is neutralization, also called acid-base titration, which involves the exchange of protons between an acid and a base, as in the reaction of hydrogen ions with hydroxide ions to form water. The second class is precipitation, where the reaction forms an insoluble solid mass, written simply as A plus B giving AB solid salt. The third class is complex formation, also known as complexometric titration, which involves the formation of a complex ion, often with metal cations, such as zinc ions reacting with ammonia to form a zinc-ammonia complex. The fourth class is electron transfer, or redox titration, where electrons are transferred between species and oxidation state change. For example, when iron 2 plus reacts with cerium 4 plus to produce iron 3 plus and cerium 3 plus. Each class has its own typical applications and preferred indicators. Detecting the endpoint of a titration can be accomplished in several ways, and the choice depends on the required precision and available equipment. The simplest method relies on direct human observation of chemical changes, specifically distinct color shifts or the sudden appearance of precipitation. This is the visual method, and it works well for teaching and for routine analyses where high precision is not critical. A more advanced approach uses precision optical instruments to measure changes in light absorption or transmission at the endpoint, which gives much greater accuracy. Finally, electrical methods use specialized sensors to measure changes in electrical properties. These include potentiometry, which tracks changes in voltage using a pH electrode, amperometry, which measures sudden shifts in electrical current, and conductance, which detects variations in the solution's overall conductivity. In an industrial quality control laboratory, automated electrical detection is the standard. Indicators are weak acids or weak bases that exhibit distinct color changes directly tied to shifts in environmental pH. The selection of an indicator for neutralization titration is strictly dictated by the specific pH at the endpoint. A classic example is phenolphthalein, which transitions from completely colorless in acidic environments to a vivid pink in basic conditions. Choosing the wrong indicator would be like setting your alarm clock to the wrong time. You would completely miss the endpoint, and your calculated result would be wrong. That is why students and analysts must memorize the transition ranges of common indicators. Sometimes water proves entirely unsuitable for pharmaceutical analysis, and we must recognize this limitation. Water fails when we encounter substances that are essentially water-insoluble, or extremely weak acids or weak bases that cannot fully dissociate in water, or complex mixtures containing compounds with highly similar dissociation constants. In these situations, we turn to non-aqueous titration, which deploys specialized organic solvents to analyze compounds that resist standard aqueous environments. This approach bypasses water's chemical limitations entirely and is essential for analyzing many raw drug substances, particularly weak amines and weak phenols. Non-aqueous solvents are classified into 4 categories based on their behavior toward protons. The first category is aprotic solvents, which are chemically neutral and neither donate nor accept protons. Examples include toluene and carbon tetrachloride. The second category is protogenic solvents, which are acidic and capable of strongly donating protons to enhance the basicity of weak bases. Examples include sulfuric acid and hydrogen fluoride. The third category is protophilic solvents, which are basic and have a high affinity for accepting protons, thereby enhancing the acidity of weak acids. Examples include liquid ammonia and various amines. The fourth category is amphiprotic solvents, which are versatile and capable of both donating and accepting protons depending on the analytical environment. The most common examples are alcohols. Choosing the right solvent can make the difference between a successful titration and a failed one. At this point, you should see that pharmaceutical analysis is not a single recipe, but rather a decision tree. The analyst must ask a series of questions. Is this a qualitative or quantitative problem? Are we working at the micro, semi-micro, or macro scale? Is the sample water-soluble or not? Will titration work, or do we need chromatography or spectroscopy? The method must be matched to the molecule, and one size definitely does not fit all. A skilled analyst thinks like a diagnostician, choosing the right tool for each unique sample. We now turn to chromatography, a family of separation techniques that began in 1900 when Mikhail Tswett pioneered the method to separate plant pigments. Chromatography separates mixtures based on their precise distribution between a stationary phase and a mobile phase. The stationary phase is typically a solid or a liquid coated on a solid, and the mobile phase is either a liquid or gas. Compounds that interact more strongly with the stationary phase move slowly, while those that interact less strongly move quickly. This difference in migration speed is what allows us to separate complex mixtures into their individual components. Every chromatographic system shares the same basic anatomy regardless of its specific type. There's always a stationary phase, which acts like the road that holds back compounds to varying degrees. There's always a mobile phase, which acts like the carrier that pushes or pulls the compounds along the road. And there is always a detector, which sees each compound as it exits the system. The output is called a chromatogram, which is a graphical representation with time on one axis and detector response on the other, and each peak in the chromatogram represents one component of the mixture. Retention time is the single most important piece of information from a chromatogram, and it is defined as the time a compound spends in the column from injection to detection. The more a compound interacts with a stationary phase, the slower it moves, and therefore the longer its retention time. This is how we identify unknown compounds. We compare their retention times to those of known standards run under identical conditions. Additionally, the area under each peak is proportional to the amount of that compound present, so a single chromatographic run can provide both qualitative identification and quantitative measurement simultaneously. Chromatography can be classified in several ways, creating a taxonomy of separation methods. One major branch is planar chromatography, where the stationary phase is flat, as in thin layer chromatography and paper chromatography. Another major branch is column chromatography, where the stationary phase is packed into a vertical tube. The mobile phase can be a liquid, giving liquid chromatography, or gas, giving gas chromatography. Finally, the separation mechanism can be adsorption, partition, ion exchange, or size exclusion. Each variant solves a different type of separation problem, and the analyst must understand them all. Two foundational adsorption techniques are thin layer chromatography, or TLC, and column chromatography. TLC is a planar technique performed on a glass plate coated with an adsorbent like silica gel or alumina. You spot your sample at the bottom, place the plate in a developing chamber with solvent, and watch the spots rise. TLC is fast, cheap, and excellent for rapid screening of non-volatile mixtures. Column chromatography, in contrast, uses a vertical glass column packed with the same adsorbents. You pull mobile phase through the column and collect fractions as they emerge. The key difference is that column chromatography allows for the physical recovery of individual components, whereas TLC is typically used only for visualization. Gas chromatography, or GC, uses a gas as the mobile phase, typically helium or nitrogen, and the column is housed inside a temperature-controlled oven. Because the mobile phase is a gas, the sample must be volatile or must be chemically converted into volatile derivatives before analysis. Two rules govern retention in gas chromatography. Rule 1 is that the polarity of the stationary phase strictly controls separation efficiency. Rule 2 is that a higher affinity for the stationary phase results in delayed elution, meaning a longer retention time. GC is the method of choice for analyzing low molecular weight gases and volatile organic compounds. High-performance liquid chromatography, or HPLC, is an advanced, high-pressure improvement upon traditional column chromatography. Instead of relying on gravity to move the mobile phase, HPLC uses high-pressure pumps to force the liquid through a tightly packed steel column. This high pressure, which can reach 400 bar or more, allows for much faster separations with much higher resolution than gravity-fed columns. HPLC is ideal for non-volatile and thermally fragile compounds, which includes most pharmaceutical drugs. We can run HPLC in normal phase mode with a polar stationary phase, or in reversed phase mode with a non-polar stationary phase, and reversed phase HPLC is currently the gold standard for pharmaceutical quality control. Let us summarize the techniques we have covered so far. Non-aqueous titrimetry, or NAT, is a bulk assay method primarily used for raw drugs, weak bases and weak acids, and amines such as captopril. Thin layer chromatography is a planar adsorption method used for rapid screening of non-volatile mixtures. Column chromatography is a vertical adsorption method used when you need to physically recover individual components. Gas chromatography is a gas partition or gas-solid method used for low molecular weight gases like carbon dioxide and hydrogen sulfide, as well as other volatile compounds. An HPLC is a high-pressure partition method used for precise separation with adaptable polarity, whether normal phase or reverse phase. Each technique has its primary use case, and knowing which to choose is the mark of a skilled analyst. We now move to spectroscopy, which we can think of as molecular interrogation, decoding structural secrets through light-matter interactions. Where chromatography separates mixtures, spectroscopy identifies individual compounds by their interaction with electromagnetic radiation. Spectroscopy tells us about the bonds present, the functional groups, the electronic environment, and even the three-dimensional conformation of a molecule. It is like giving each molecule a unique fingerprint based on how it absorbs or emits light. Every spectroscopic experiment follows the same three-step pattern. First, we apply controlled electromagnetic radiation to the sample, choosing a specific range of frequencies depending on what we want to learn. Second, the molecule absorbs specific frequencies based on its internal structure. Each absorption event corresponds to a particular energy transition, such as an electron jumping to a higher orbital or bond vibrating more vigorously. Third, the instrument records a unique diagnostic fingerprint of the structural interaction, which we call a spectrum. No two different molecules produce exactly the same spectrum, which is why spectroscopy is so powerful for identification. Ultraviolet visible spectroscopy, or UV-Vis, uses high-energy wavelengths in the range of approximately 210 to 900 nanometers to probe the outer electrons of a molecule. The physical target is electronic transitions, meaning electrons moving from a lower energy orbital to a higher energy orbital. The primary identification feature is the chromophore, which is any part of the molecule responsible for absorbing UV or visible light. Common chromophores include carbon-carbon double bonds, carbonyl groups, and aromatic rings. UV-Vis is fast, simple, and highly sensitive, making it ideal for quantifying drugs that contain chromophores, such as paracetamol. Infrared spectroscopy, or IR, uses lower-energy thermal radiation to map the mechanical vibrations of chemical bonds. When infrared light of the correct frequency hits a molecule, bonds will stretch, bend, rock, or twist. Each type of bond and each functional group absorbs at a characteristic wave number, typically reported in reciprocal centimeters. For example, a sharp peak around 1700 reciprocal centimeters tells you a carbonyl group is present, while a broad peak around 3300 indicates an alcohol-OH bond. IR spectroscopy is the go-to method for identifying functional groups in an unknown compound. Nuclear magnetic resonance spectroscopy, or NMR, is the most powerful structural tool in the pharmaceutical analyst's arsenal. NMR uses radiofrequency radiation to probe the atomic nuclei under the influence of a strong external magnetic field. The most commonly studied nuclei are hydrogen-1 and carbon-13. When the sample is placed in the magnetic field, the nuclei align with or against the field, and then radiofrequency pulses disturb that alignment. As the nuclei relax back to their original state, they emit signals that reveal their chemical environment, including how many neighboring hydrogens are present and what atoms are nearby. NMR provides detailed conformational and structural information that no other single technique can match. If we compare the three main spectroscopic techniques across the electromagnetic spectrum, we see a clear pattern of complementary strengths. UV-Vis uses electronic energy to target outer electrons and identify chromophores, operating in the range of 210 to 900 nanometers. Infrared uses thermal or vibrational energy to target molecular bonds and identify functional groups, operating in the range of 4,000 to about 1,300 reciprocal centimeters. An NMR uses radiofrequency or magnetic energy to target nuclei, typically hydrogen-1 and carbon-13, and it maps the full conformation and structure of the molecule. No single technique gives you the complete picture, which is why a full characterization often uses all three. In conclusion, spectroscopy is the final identifying step in a broader quality control workflow that includes chromatography and often titration as well. In a real pharmaceutical quality control laboratory, you would typically use chromatography, especially HPLC, to separate and quantify the components of a mixture. Then you would use spectroscopy, particularly IR and NMR, to confirm the identity and purity of the isolated components. Together, these analytical frameworks form the holistic laboratory ecosystem that ensures every medicine reaching a patient is safe, effective, and consistent. Thank you for your attention. I hope you have learned something about pharmaceutical analysis.